buddy. Okay, I think we got people logged in that are going to be here for live video. So today we're going to dive into slide set 2.1 for most of the class. But before that, I want to ask if anybody had any questions about the statics practice problems or had tried any of those, had any questions or concerns about those. I'm thinking most of us that are here probably took the 2000 statics class during your refresher quarter, so probably up to speed on that, and or it's still fresh enough in your mind. But if you do have any questions about those, we can discuss those anytime. The solutions to all those are in this 1.3 handout, so those are available whenever you want to look at them in set 1.3. All right. So I'm going to jump into slide set number 2 today. We're going to talk about stress and strain. We probably already have a basic understanding of those things, but because some of us might be a little bit rusty, we're still going to start from scratch and quickly review the basic undergraduate stuff, and then we'll work up to looking at some stress transformations, give us a chance to use that transformation matrix that we learned last week. All right. So stress and strain are, of course, important components in describing a material's response. It's somewhat similar to Ohm's law. If there are any electrical engineers, if V equals IR, you could kind of be analogous to sigma equals E times epsilon. Or in terms of a spring, force equal K times delta. Epsilon's kind of like our elongation. In fact, it's a percentage elongation. Stress is measured from force. It's a force per area. And then our Young's modulus is kind of like the stiffness. So remember, our basic definitions for stress is force per unit area. Basic definition for strain is deformation per unit length. And we're going to look at transforming those between coordinate systems, getting the general Hooke's law relationship between the two for different kinds of materials, and then setting up problems with different boundary and compatibility conditions. All right, so first, our basic definition of stress. If we take any old slice or cross section through a material, we've got some forces on there, and we look at some small area delta A. So some small finite area delta A, and there's some finite force delta F passing through that. Then our stress at that spot, at that location P, this small finite area, is delta F per delta A. And our formal definition is as we make that finite area really, really small, as delta A goes to 0, that's going to be our stress at a point. Basic units, PSI or pound per square inch. We're also going to see KSI. That's fairly common in a lot of large structures like ships. We deal in thousands of PSI. And yield stresses. Often we might say a yield stress of 36 KSI if we buy A36 structural steel. Or in shipbuilding, we use a lot of the HY and HSLA. Have you heard those names before? Maybe seen them on a ship drawing. So those HY or HSLA preceded by a 2 or 3 digit number, that's going to be our yield stress in KSI. So if you're working with HY 100, we know it doesn't yield till we pull it to 100,000 PSI. All right, so KSI and PSI. And then pascals or Newton per meter squared is standard. Also convenient because of the scales that we work on, MPa or Newton per millimeter squared, or 10 to the 6 pascals is one that we might see often. We often see yield stresses in metric in MPa. Two kinds of stress basic is normal and shear. Normal is going to be that acting perpendicular to a cross section, either in or out. And then shear stress acting parallel to that cross section. So on that little slice delta A, we can break up that differential force into a perpendicular part that's either out or in, and then a parallel part that's moving along that little slice of area. So our normal stress is going to be the perpendicular force per area, shear stress, the shear force per same area. And our subscripts generally, if we see same subscript or just one script, so sigma xx or just sigma x or 1, 1 if we're in the 1, 2, 3 instead of x, y, z, same thing though. That's going to be our normal stresses. And then if we see two different subscripts, that's going to clue us in that we're looking at a shear stress. So tau xy or sigma xy or sigma 1, 2. Anytime we have different subscripts, we know we're dealing with a shear stress. Now, talking about stresses and where do we put them on a differential element. So let's say we take a look at a small differential volume, a little cube with x, y, and z axes. So I'll have x out, y horizontal, and z up. Our basic sign convention and naming convention is going to be that the first letter is going to tell us what plane we're on. All right. Was somebody in the back mind just dimming the lights a little bit? So our first face that we're going to look at, the x face, that's going to be the green one on your slide there. And we can see this green face is actually YZ in terms of plane. We see it's Y in one direction, Z in the other. But when we name these planes, we want to name it with as quickly as possible with only one letter. So we're naming the plane that's perpendicular to the axis. So the x plane, quote unquote, is a plane that's perpendicular to x. And we see all this green plane is perpendicular to that x-axis. So sigma xx, tau xy, tau xz are all going to be on this green face. The first letter tells us which face to be on. Likewise, the y plane is going to be this blue one on the right. All of that blue plane is perpendicular to y. And then tau yx, sigma yy, tau yz are all going to reside on there. And then on the top, on the red face, that's perpendicular to z. So all those first subscripts are going to be z. So first subscript tells us what face are you on, and then the second one gives us the direction of the stress. So on our green face here, we've got sigma xx, x face, x direction. Tau xy is going to be on the x face, but in the y direction. And then xz, we're still on that x face, but we're going in the z direction. Moving over to this one, we've got tau yx, y face x direction, y face y direction, and then y face z direction. And same story up at the top there. All right. So first one will tell us the face we're on. The second one's going to tell us which way to point the arrow. That's our XYZ frame. If we're using the X1, X2, X3 or 1, 2, 3 coordinate system, and for the index shorthand, same difference. Our number one's going to be all those arrows on the green face, and they're in the 1, 2, and 3 direction. And then 2, 1, 2, 2, and 2, 3 are all going to sit on the blue face, and on the red face, we got 3, 1, 3, 2, and 3, 3. So that's our naming convention. First one tells us where we are, and second one tells us which direction to point that arrow. Now, these could all be a plus or minus of the arrows that we're looking at. So if the stress is in the same direction as these arrows we've drawn, if it's in the positive direction, then we'll get a positive sign on it. If we get a negative sign on the stress in the normal direction, that's going to mean we get a compressive stress into, right? So tensile stresses for the three normals, XX, YY, and ZZ, are going to be out of the page as drawn. And if they're negative in value, then that just means they're going into the cube instead of out. Right? And same story with the shears. If we get a sign as indicated, it's going to be in the direction of the second letter. And if we get a negative value for tau xy, then we know it's going to the left instead of to the right on that front face there. So here's our positions for the stresses. And then on the backward faces, we get the same kind of deal, but it's going to be in the opposite direction. So we just looked at everything on the front faces. Let's go just take a peek on the back here. And I'm going to draw out one of these. Let's just look at the X face. So on the X face up in the front here, with what we had tau xy going that way, we had sigma xx going out, and we had tau XZ going up, all right? When we're on the back face, we're back here in the negative X face on the back side there with Y here, Z here. And then we also know that going down would be negative Z and going to the left will be negative Y. When we're talking about that back face, that's going to be this one back here. On the negative X face, our sigma XX is going to go this way. It's going to be the same value as it is on the front, but going back. So if we're on the minus X face, we put it in the minus X direction. We're also on the minus X face, so tau XY on the back is going to go in the negative Y direction. And likewise, tau XZ on the back is going to be going down. The tau XY, tau XZ. On any of the three back faces, the back, the left side, or the bottom, we just switch the direction. So front face, positive X, and positive for all the directions. On the back one, we're on the negative face, so we put arrows in the negative direction. And this should kind of be intuitive to us because this cube's supposed to be in equilibrium. So if we have sigma XX this way on the front and back on the back, then that's going to be an equal pull. The front face and back face are the same area if it's a cube. So we'll be in force equilibrium between those two. And same thing with the shears. We could see one moving left, one moving right. And with the XZs, one's moving up, one's moving down. So this keeps us in equilibrium by having the back ones backward. And we can also think about it, front face, front directions. If we're on the back face, everything goes in a backward arrow direction as well. All right. And then same story on the bottom and on the left side. We'll just draw this front and back for illustration. All right, so there's our basic sign convention and naming convention. And we might see these stresses shown in different ways.
Really quick before you move on.
Yeah.
Is it,
Hold on just a second. I want to make sure your question gets picked up there.
so this shows for the XYZ frame, it uses sigma and tau, and the X1, X2, X3 frame, it uses sigma like 3-2 for the shear stresses. Is this just an example of possible ways it could be indicated? Or
Yeah,
that
so on
practice?
On the next slide, we see in some of the more basic solid mechanics textbooks, you're probably going to see all the shears written as tau, all right, which makes it real clear that it's a shear. But anytime we have two different letters, whether it's tau or sigma, that's going to be a shear for us. All right. So in the intermediate type books, you're probably going to see them all written as sigma because they're all part of this stress matrix or tensor right here. XX, XY, XZ. Each row is going to be one of the faces that we looked at on the previous page. So we've got the green face going. Green face is going to be this row right here, the one that we looked at. All right. And then on the Y one, the blue face, those are going to be the stresses that make up the second row right here. And then our Z face, or the red one, is going to be the ones that make up the third row there. So here's our X face, Y face, and Z face. And remember, first subscript, when we were looking at index stuff, the first subscript told us the row. So here's the face that we're on is going to be X, Y, and Z, the row number. And then the column is going to tell us the direction for the arrow. That's going to be X, Y, and Z across the top. So we might see taus in our introductory textbooks for that. Some books will also use all sigmas, but the subscript is what tells us the important thing. If it's the same, that's going to be a normal stress. If they're different, it's going to be shears. So the diagonals are going to be our normal stresses, and then the shears are going to be the off-diagonal values. And each row is one of those faces that we looked at on the previous page. So the green face and the blue face and the red face. All right. If we write it in the index type notation with 1, 2, and 3 taking the place of X, Y, and Z, same story. First subscript is the face. and second subscript is going to be our direction. So those are three different ways of writing the same thing. It just depends on what book or text you're looking at as to what they use for the shears, whether it's tau or sigma. But the subscript will tell you the whole story, where you are and what way to point the arrow. All right, let's talk a little bit about that stress tensor. We just saw right here that it's got 9 components. We saw 3 front faces and then everything mirrored in reverse on the back faces, the back, the left, and the bottom. So those are 9 total components that we have to work with, 3 directions on each of the 3 faces, right? And we can show that actually only 6 of those components are going to be independent because of some symmetry. What we're going to find out is that everything across the diagonal, sigma xy and sigma yx are going to be the same, xz and zx, yz and zy are going to end up being the same. So out of these 9, we only need to find 6 of those components to get the whole picture, right? Now, let's take a look and use our statics practice here to come up with that, and we'll also figure out our stress equilibrium this way. So let's think about a 2D case. We'll make it a little bit simpler, and then we could flip it back up to 3D after we're done. Let's think about a cube just like this in the XY plane. And we're going to look at stuff that's on the front and the back and on the top and on the bottom. We're not going to pay attention to anything coming out of us in that Z direction. So just for our in-plane stresses, ones that are acting within the XY plane, we've got our sigma XX. And if we go some finite distance, that stress may not be the same on both sides. In this tiny little cube that we looked at back here, if this is a really small one, same stress on the front and back. If we expand that out to some finite size, we could have a change in stress as we go across this X distance here. Right. So sigma XX, what we have on the left side, and then any change with X, change in stress with X, times some distance across there. So that distance that we're talking about so some distance across here, and we'll call that dx. So we think about that mathematical Taylor series at some spot plus the slope or change times the distance along that axis. So that's what we're doing here. Sigma xx, whatever it was on that left edge, go some distance dx, and then times the slope of the stress if there's any change between the left and right side that's captured. And we could do the same thing with tau xy, x face y direction, down on the left side. We go from the left to right edge, and we might have some change in shear with x times that same dx distance. And then we do the same thing going from the bottom to the top. On the bottom, we've got sigma yy. It could change on our way up. So if we go some distance dy right here, those stresses on the bottom could change going from the bottom to the top. So sigma yy, then some change in that stress with y times the dy distance. And same story with the yx shear, could change going from the bottom to the top by that much. Right. So this is for a finite cube, and then some thickness out of the page, pz. And we've got a possible change in stress from left to right and from bottom to top. So here's our free body diagram right there. And our equilibrium equations are still the same as they are in statics. Some forces x, some forces y, and then some moments about out of the page z. So let's say we look at the sum forces in x first. Which arrows do we have going in the x direction? Well, sigma xx for sure. And then also tau yx. It's on the top and bottom, but it's still moving in the horizontal direction. So if we take the normal stress on the right, sigma xx plus any change, times the area, that's going to give us the force on the right-hand side. So on the right-hand side, we're dy tall by dz out of the page. So that dy by dz is going to be our area. So we have stress times area on the right side from the normal stress. And then we're going to take away the stress times the area on the left. Sigma xx on the left is going in the negative direction, so we'll put a minus there. And the left and right side have the same areas, dy tall by dz out of the page. And then same story with our shear on the top and the bottom, tau yx plus any difference on the top, and that's dxy by dz out of the page. And then minus the tau yx on the bottom times that same area, top and bottom of the same area, is dx across by dz out of the page. All right, so this force summation has to add up to 0. And we can subtract, we can take off the sigma xx in both the positive and negative term, and the tau yx is also going to fall off. And then also if we have any body force like gravity or things like that, a force per unit volume, body force can go right here, and then that's going to be times the volume of the cube, dx, dy, dz. So that last term right there is going to be body force, like a gravity or a centrifugal type load, times the volume, because if that body force is in the x direction, that's also going to add to the net on the object. So there's our force balance. We got this stress on the right-hand side, the left-hand side, the top and bottom, the 4 arrows that move left or right, and then any body force like gravity or etc. And we see we can divide through by dx, dy, dz because all 3 of those show up in this spot and in this spot. And after we cancel off the sigma xx and the tau yx terms, we can divide on through. And what we get is partial sigma xx, the normal x stress with x, plus partial tau yx with y, plus body force in x per volume equals 0. All right. So this is what's required. This is how the stresses can change, and we're still having this box in balance, not flying off to one side or the other. We can do the same thing and sum up the y forces. So we've got sigma yy plus the differential times our top face, dx by dz. Then on the bottom, we got sigma yy times the same area, dx dz, that's a horizontal slice out of the page. And then tau xy on the front and the back face, the right and left face. So on the right side face, we got tau xy going up plus differential. And then the area on the right is dy dz, that's a slice coming out of the page on the right. And then minus tau xy, the left side's pointing down, dy dz, same area. And then body force, if our gravity force is centrifugal or gravity or anything like that, any kind of body force load acceleration is going to go there. And then we've got per unit volume times dx dy dz gives us our force. And that also has to add up to 0 or this thing will start flying up or down. So again, we can cross off the basic values, the ones that don't have a derivative. And once we do that, everything has a dx, dy, and a dz. This one, and the body force. We can divide out by that. And then we've got partial sigma yy with y, plus partial tau xy with x, plus body force in y equal to 0. So that takes care of 2 of our things. This makes sure that it's stationary for translating left or right, or up or down. Our forces equal 0, then no acceleration, and we're static. And then the third thing that we have to work with is sum of moments equal to 0. Now, if we think about the XX and the YY stresses, on the left or the right side, those normal stresses are going to pass right through the middle. All right, they're the same value going all the way across there. Well, let's take a look at a little 2D. We look at our 2D cube. On the bottom, we've got sigma yy like this. We got on the top sigma yy plus that differential stuff on the top. But it's the same all the way here and here. And so our centroid of that force is going to go right through the middle. If it's same all the way across, the net force is going to pass right through the middle. So in terms of creating a moment about z, where z's out of the page, if you pass right through the z-axis, you don't create any moment about it. So these normal stresses aren't going to do anything. Likewise, our sigma xx plus that partial stuff on the front and sigma xx on the back, same all the way up and down the left and right face. So those net forces are also going to push right through the middle. Doesn't cause any spinning counterclockwise or clockwise about z. However, our shears, like the tau on the front, tau xy plus the differential stuff, and on the back side, we've also got tau xy back here going down. We could see that all of that resultant is going to be right here and right here. That's going to be some distance away from the z-axis. So these two are going to give us some stresses. Here we got dx over 2 and we got dx over 2 here. Those are going to be our moment arms, right? And then on the top, I've got tau yx plus the differential stuff, and that's going to be going this way. And then on the bottom, I've got tau yx. That net force with the, multiplied by area is going to be going to the left. So those are each going to have a dy over 2. And I can see that if I put my z-axis out of the page, the tau xy's on the right and the left are both going to spin it clockwise. Front one's going to push clockwise or counterclockwise, sorry. Bottom one's going to push counterclockwise, or a positive rotation with our right hand. The yx on the top and the bottom is going to push clockwise or give us a negative moment rotation. So this is going to give us a plus moment. This one's going to give us a plus moment. These two both turn clockwise. So this is a negative moment and a negative moment on these two. So this is what we've got to balance. We've got to balance these two and these two. And if those are balanced, then our cube does not spin or rotate about the outer page. So let's see how that equation sets up. We've got it written out on the slide there. Our tau xy on the right goes counterclockwise with our moment arm of dx over 2. So we got the stress times the area, just like before, when we were summing it up as a y force, times the moment arm perpendicular, that's dx over 2. And then the left side also contributes counterclockwise, or right-hand rule out of the page. So that one's a positive also. We've got the force times the moment. And then the top one, tau yx plus the differential times the area, there's our force. dy over 2, it gets a minus sign because the top is going to push us clockwise around the middle. And the bottom also pushes us clockwise. So that's against our right-hand rule. It also gets a negative sign. So there's our summation of moments. It's basically the force shears that contribute to that. And we can sum that one up. We got tau xy, dx, dy, dz. We've got the differential one right over there. That one is going to be times a half because it's only here. The tau's in both places, so the dx over 2 just becomes a dx for that one. And then same story with tau yx. It's in 2 places, so that 1/2s go away, and then we're left with a half on the differential part. We can divide that through by the dx, the dy, and the dz, crossed off a bunch of those. And then we take our limit as dx and dy get really small. So as we make this cube kind of small, we can get the differential parts to fall off. And what we're left with is tau xy equals tau yx at a single spot. All right. And this kind of makes sense because we can see that those have an equal moment arm So if they're gonna cancel each other out, they probably gotta be the same value, right? Or if we're talking about a cube, dx and dy are the same lengths for these moment arms, then the values of those shear arrows should be the same. That's going to keep us in balance, right? Top and bottom are going clockwise, the left and right are going counterclockwise. And if they're the same value and they're the same distance from the origin, then we don't get any spinning. So that summation of moments is what tells us then on the previous slide over here that our shears are going to be symmetric. Sigma xy is sigma yx. And then in the 3D case, xz and zx, yz and zy would also be the same. So our symmetric line is going to be short, long is the symmetric line. Here's our symmetry for the stress tensor. Normals or whatever they are, and everything across that diagonal there is going to be symmetric or the same value. We just proved it for xy and yx, tau xy, tau yx, or sigma xy, sigma yx, but it's also true for the other ones if we were to draw those arrows around the y-axis and about the x-axis moments. We could prove that. All right, so that one gives us our symmetry, and then the other two that we're left with is our stress equilibrium equations. We got xx with x right there. And then since we just proved this one, we're going to put this one to work right away. We'll put an xy in there for yx and say xy with y, and then plus body force in x equal to 0. And then for our y direction, we've got yy with y, we've got xy with x, and we've got body force in y. And these shears are interchangeable. So this is our stress equilibrium. This is how the stresses can change as we go through the body, and it keeps that cube balanced. So this is one of our basic important equations for solid mechanics, our stress equilibrium. And if we take that 2D and just add the third term, so we saw xx with x, xy